So, cryptography, right? We've kind of gone over basic computer security. Now we want to look at how we can actually go ahead and communicate securely without someone eavesdropping on our information. So, let's start out with a simple example. Can I get 2 volunteers from the audience? Awesome. Sarah and Grant, come on up. In cryptography, it is the convention that one person talking is Alice, the other is Bob. So Sarah, you are now Alice, we'll get you to stand over there. Grant, you are now Bob, we'll get you to stand over there. You don't have to be all the way over there. So, Bob, you are now going to tell Alice how many siblings you have. But you can't let the class know. The class is Eve, so named because the class is an eavesdropper. You are trying to let Alice know how many siblings you have, right? If it's none, then the answer is 0, without letting Eve know. Go. No, Alice, you got to stay there, right? Yeah, you can't go ahead and fly to England if you want to communicate securely with the server there. Okay. Yeah. Oh, okay. Oh, so one of our Eves saw it, so that's not going to work. So yeah, you kind of tried to hide it there a little bit. So you're trying to use sort of a secure channel, right? Making it, put your hand here so it's only visible on this side of the room. But unfortunately, one of our Eves saw it, right? So Eve, what is it? 1. Alice, is that what you got? Yeah. Bob, is that correct? Yeah. It is actually almost impossible to do that. It is impossible to do it completely securely using classical methods because Alice sees everything that Eve sees, right? You have nothing that you can use to tell just Alice and not Eve. I'm now going to give you an X. So your X is that number of fingers, right? So binary 0, 1, 0, 0. Okay? Alice, I'm going to give you the same X. So your X is that number of fingers, right? Binary 0, 1, 0, 0. You guys both have your X? Now, Alice is going to tell Bob how old she is in terms of X, right? So it can be some kind of expression, gives your age as a function of X. Okay, so you can say it out loud, right? The class can hear?
4 times.
So 4 times X, you mean? Okay. So Bob, you get 4 times X, and what do you deduce Alice's age is from that?
16.
You get 16. The class had no idea, right? They could have guessed it's probably not 12, it's probably not 20. Yeah. Right? But you guys can see that, like, had she done, say, 12 plus X, then you'd have had no idea, right? So there are ways of using that X to make it so the class really can't tell. Make sense? So that X is what we call a private key, right? That is a key that both parties communicating have, no one else has, and we use that to encrypt our data. So the reason cryptography is important is right now Alice and Bob can walk up to each other and talk to each other, right? But they might be an ocean apart. So that is sort of the motivation there, right? So remember way back to when we were looking at our IP protocol. So we have our servers in Toronto goes to the ISP, the Regional Internet Registry. This cross-Atlantic cable gets to the English, or the Russia and Europe Internet Registry, gets to Oxford's IP, and gets to Oxford server. In U of T, it goes through all of these different switches, right? Any one of these switches, these servers, these can all see your data because your data is a bunch of headers and plain text. Goes in plain binary. Anyone with access to any of the physical Ethernet cables can tap that cable, analyze this Ethernet header, get your data, and send it along without anyone being the wiser, right? So anywhere on that path from here to England, if Alice is over in England and Bob is right here, someone can intercept that number and get it, right, and read what could potentially be very private data. So we want to do something to encrypt this data to make sure that that can't happen. Any questions so far? So the way we encrypt our data in practice is with HTTPS, stands for HTTP Secure, and it uses a shared private key. Yeah, thanks guys. It sends over the network with the encrypted data, right? So instead of this, with this stuff right here, we would see this with a bunch of gobbledygook right here. Okay? That gobbledygook, we can read that, but we have no idea what it means because we don't have the private key, so we can't decrypt it, so we can't read the number that's being sent. And our private key is a lot longer than 4. 4 was the X value. It is like the PEM and PPK file that you guys use to SSH in. So why don't you go open your desktop and take a look at those files. Right, so Alex asked a very good question. He said, is it a shared private key? Because wouldn't you need a separate key for each user? Why not make it asymmetric? The answer is yes. You guys have no idea what asymmetric means, however. We'll be getting to that in a bit. A shared private key is used for SSH. So you have to have the same exact key on both client and server. This is just an example of what a key looks like in practical cryptography. We use a slightly different one when we use HTTPS. This is an SSH key. So yes, the answer is it is a shared private key, and for HTTPS we do use asymmetric encryption that class will get to in a couple minutes, maybe after lunch. Right, so what we see here, a bit of header, right? We say what type of encryption it is. We give a comment there, and we say how many lines of it are in. So we have a public-private key. We'll learn about what those mean in a bit. And we have all this random text. So what we do is we convert binary, right? So our key is a binary number. We convert it into text here. So we use ASCII to convert or to encode our binary. And that stores our key. Our key is a big, long binary number. It's a very big number stored like this. Right? So like we were using 4 before, if we use a large number and a slightly stronger method than 4 times x, we can make it very difficult for the other side to guess based solely on what we send. So our end goal is to understand how this works. And to do that, we have to look at some of the basics of cryptography. So cryptography is a mathematical area of study. There is mathematical nomenclature that goes with it and conventions. We have a couple words that we need to know. So the first thing is what it's concerned with. One is encrypting and decrypting messages, what we've been looking at before. Second is authenticating recipients. We do that to make sure that we're communicating with the right party and not someone pretending to be Alice or pretending to be Bob. Both of these can be cracked to gain access to an encrypted system. A code is what we call replacing each word or other semantic structure, right? So code words is an example. This is a little comic by XKCD. Who's heard of that before? Yeah, of course Sarah has. Anyone else? Alex? XKCD is an excellent webcomic strip. It does a lot of comics on sort of intellectual topics like this, right? So someone's actually saying the eagle has left the nest, but it sounds like a secret agent code, so this guy's mocking her about that, right? So that's an example of a code. Eagle has left the nest, you agree beforehand, means something. What we normally use in computers is not that, because that only works on English, and it's not very versatile. We use ciphers. A cipher replaces individual letters, right? So let's look at a couple. Or before I do that, let's look at the math behind it. So you guys all know the Latin alphabet, right? The one we use for English, A to Z. Anyone know any other alphabets? I'm hearing some things. Can't quite tell what you're saying, though. Greek? Yeah, Greek's one. Nicholas? American Sign Language? That's a good one. Anything else? Anyone speak Russian or an Eastern European language? They use Cyrillic. Alex?
Yeah.
Okay, yeah. Yeah, so you're going to say that? Yeah, so we have a bunch of different alphabets that we use in languages. We also have a bunch that we use in cryptography. So the binary alphabet is just 2 letters, 0 and 1. right? The Latin alphabet is ABC to XYZ. I'm just saying capital here to include both caps and non-caps. You can do either, have two different alphabets of different sizes. Hi. Yeah, we have a class in here. You can use the computers on that far row if you don't mind the stuff going on. Yeah, so alphabets can be anything. Normally we use letters that we can see. And a string, right? We know that a string in Python is a list of characters. It's a list of elements of that alphabet. So Billy is a string on the Latin alphabet, and this binary number here is a string on the binary alphabet, right? And we have sigma represents that alphabet. So sigma represents the set of possible letters that we can use. Sigma superscript n represents the set of all strings of length n. Right, so we can see all sigma 2 on the binary alphabet only has 4 options. And we can have our sigma of the Latin alphabet. Tree is an element of sigma 4. So that is an element sign. It means it's part of that set. Sigma 4 is the set of all possible strings of length 4. And for any alphabet, sigma 0 is just the empty string. Questions on that? Right, almost done with this math stuff. So sigma star represents the strings of any length, right? So if we use the binary alphabet, then we can have sigma star as a set of all binary strings. And we can also just write directly 0, 1 star. Anyone want to take a crack at what this means? If you get it, I have a prize for you. Anyone know what some of those individual symbols mean?
Upside down A is for all.
Yeah, so upside down A is for all. Sarah, you have something? Yeah, so n is an element of the natural numbers. What does sigma n mean? Yeah, so the set of n what? Not, yeah, so the set of n length strings. Right, so sigma n is a set of n length strings. What sigma star mean? Any length strings. And what's this little symbol mean right here?
Include. Yeah.
So include, you're almost there. The word we're looking sorry? It's not excluded. The word we're looking for is a subset.
Oh.
Yeah. So this is a set of all possible strings on sigma. This is the strings of length n. Strings of length n is a subset of all possible strings on sigma. And we add this for all n is an element of integers, just because sigma to the 2.5 makes no sense.
What does the upside down A mean?
The upside down A stands for all. So it says that's true for all n is an element of integers. If n is not an integer, nothing is said about this relationship. Right? So that's a bit of mathematical formality. We won't be doing too much math in this course. A simple cipher goes ahead and replaces one letter directly with another. And we use what's called an encoding function for this. So it takes a character X and returns its encoded version. And the decoding function does the opposite, right? And it makes sense that when we decode the encoded character, we get the original character. So we can say that d of e of x equals x, which means they're inverses. So a last thing that we can do is use different alphabets, right? So a very simple one, we map 0s to 2s and 1s to 3s, and we can convert this binary number to this string. It's a terrible code, or sorry, a terrible cipher, but it is an example of converting from one alphabet to another. Right? So we have two different alphabets here, sigma 0, 1 and delta 2, 3. And we see that the encoding function maps from one alphabet to the other. The decoding function, of course, maps the other way. Questions on that? So let's look at a practical example, because all this math is getting a little bit boring. One of the first examples was from Julius Caesar. Anyone know who Caesar was? Francois? Yeah. Yeah, so he did live about 50 before Christ. He wasn't actually a Roman emperor. That's a common misconception. He was, yeah? Yeah, so as Sarah was saying, it was a guy named Brutus. conspiring with a guy named Cassius to stab him, and his death led to the lower classes of the Roman population who liked him because he was good to them, getting very annoyed, and they overthrew the Roman Republic, and that led to the Roman Empire. So Caesar laid the stone in his death, I suppose, for the Roman Empire. He was not the first emperor. His grandnephew was. But we get the month of July from that because he established the Julian calendar and named a month after himself. Yes? Yeah, he died on the Ides of March, at least so the legend goes. That's March 15th. Yeah, Caesar salad does not come from Julius Caesar. It comes from a guy whose first name was Caesar, who lived about 100 years ago in the States. But as a Roman general, that's what he lived as, and he had many ambitious conquests. He expanded the Roman Republic hugely, and he needed a way for his men to communicate from a distance. Judith? Oh, okay. So what he did is he used the number 0 to 26 as a key. They had a slightly different alphabet back then, but we can pretend it was with a modern alphabet. And the cipher shifted each letter up or down by that number in the alphabet. So if our key is 3, then we add 1, 2, 3 to A, we get D. So A goes to D, right? And so we can encrypt P to S. So anyone want to give with a key of 3 your name with a Caesar cipher? No? There might or might not be a prize for it. Sarah? So you're...
K.
Awesome.
The Dudic.
Dudic, you already have a squishy hard hat, right? So there is USB stick. So we'll end there for the morning. Yeah, I'll leave that up. You guys can try encrypting your name with a Caesar cipher.